So we are going to continue our discussion of periodic trends. And just as a reminder, everything has to do with that effective nuclear charge, how strongly the nucleus can hold on to its electrons. So the two trends that we're going to talk about in this video are ionization energy and electron affinity. Now, we're going to take them in pieces, and before we talk about what the trend is, we're going to define what these things are, just like we defined atomic and ionic radius in the previous video. Ionization energy is the amount of energy required to go in and rip an electron off of an atom. And so you can imagine that you can have all sorts of ionization energies. So this first row here is an atom that is having one electron pulled off, and the first ionization energy is something that has to be put in to be able to do that. Then if you have this singly charged ion and you're going to remove another electron, you've got to put the second ionization energy in, and so forth. Now, the idea, again, having to do with that whole charge attraction stuff, as you remove an electron, then again, the radius gets smaller and the nucleus has a stronger hold on the leftover electrons. Therefore, as we continue to remove electrons, it gets more and more difficult to remove the next electrons. And so in this case, the third ionization energy is going to be greater than the second ionization energy, and the second ionization energy is going to be greater than that first ionization energy. And so this table here shows us what the trend kind of looks like. And one thing that you can notice, and there are a number of reasons why we look at it in this way, but in general, right now we're going to look at the first ionization energy. And let's look at lithium, which is on the far left of the periodic table. And as we move across, we see that in general, the ionization energy increases. There are a few little drops right here between beryllium and boron, and also right here between nitrogen and oxygen. And I'm going to talk about why that is in a few minutes. What I also want you to look at is the differences between the first ionization energy and the second ionization energy, and maybe the third. If you look at lithium, for example, we have 520 kilojoules per mole, but then it jumps all the way to 7,000. Okay? And so that's a huge jump. Whereas with beryllium here, we see about 900, but then it just about doubles. Okay? And then you see a huge jump. And the reason for this difference here is because once you remove all of the valence electrons, all of the outer electrons, then atoms become very stable, or ions become very stable. So lithium has one valence electron. Once it loses that valence electron, it becomes very difficult to remove the next electron. Beryllium has two valence electrons, so it loses one, two, and then it becomes very difficult to remove that next one. Boron has three, one, two, three. It does increase, but then you see this huge jump right here. And so as you move across, once you remove all of the valence electrons, then it becomes exceedingly difficult to remove that. So again, once you remove all the electrons to give a full shell, then the atom becomes very defensive. And that's the key point to this table. Now, when we look at ionization energy, again, it goes just like effective nuclear charge. As we move across the table, then the effective nuclear charge goes up, and therefore the ionization energy moves up. The two things that I want to talk about is right here, and that's between beryllium and boron, okay, the second and third column, and then between nitrogen and oxygen. Beryllium has an outer electron configuration of 2s2, but then when you go to boron, you're going from 2s2, 2p1. So we're filling a new subshell here, and therefore there's a small dip in ionization energy. Right here, this is going to be 2p3, so it's got a half-filled shell, or half-filled subshell, and this is the first place that we have to pair. Oxygen's the first place we have to pair. And so therefore there's a little dip in ionization energy. And as you can see, This is a periodic thing because in the next row, you see the same types of things happening as well as in future rows. So again, it's filling a new subshell or when you first have to pair. And so again, ionization energy generally goes with effective nuclear charge. And so this again shows you the general trend just looking across the periodic table, and it mimics effective nuclear charge. Now, electron affinity in some ways is kind of the opposite. It's the amount of energy related to the addition of an electron. So ionization energy is removing an electron. Electron affinity is adding an electron. And so we can see here for fluorine, when you add an electron, as it turns out, the amount of energy is actually released. Okay, and you can see this is a nutty definition. It says it's the negative of the energy change, and that's because most of the time energy is released when electrons are put into play, but people wanted to make electron affinity positive. But what you can see is all we do is change the sign. So the amount of energy released when we add an electron to fluorine is 328 kilojoules per mole. So the electron affinity becomes a positive 328. And here is oxygen. And again, it is a negative value for the amount of energy released. So we make that electron affinity positive. Now, if we look at this in general, and it's not as good of a trend, but electron affinity increases as we move from left to right. And that again is a general trend. And it also increases from the bottom to the top. It's not perfect, but again, it has to do with things that have good effective nuclear charge also have really good ability to pull electrons towards themselves. And so you can see, again, in general, going across the table, we have electron affinity increasing as we move from left to right. And so that pretty much completes our discussion of periodic trends. Again, the key is effective nuclear charge. It can explain everything that we deal with here.